Welcome back to the Deep Dive, where we take a stack of dense research, technical papers, and expert notes, and really just tear into them so you can walk away instantly well-informed.
Today, we are wrestling with, I think, one of the biggest and most urgent conflicts in modern artificial intelligence.
And what's that?
It's this painful trade-off between immense power and, practical efficiency. We've seen these incredible breakthroughs with massive models, but they come with a really brutal price tag.
That's the core tension, isn't it? It's a critical challenge for anyone looking to move AI out of the cloud and, into the real world. We know current classical vision language models, VLMs, they're incredibly powerful
Oh,
generalists.
for sure. They can see and reason.
But they are computational behemoths. They gulp down resources, making them slow, cripplingly expensive to train, and often totally unusable for real-time applications.
Think about the applications where speed and efficiency are just non-negotiable.
Like,
A robot making a real-time decision on a dynamic factory floor. Or maybe a pair of smart glasses that's constantly summarizing and interpreting the world around you. For those tasks, the existing architecture of these state-of-the-art models, it fails.
they have built-in fundamental problems.
Exactly. Architectural problems that prevent real-world deployment at scale.
Exactly. And the source material we have today, a dense stack of papers from Meta AI Research, lays out the architectural answer to this fundamental problem. We are diving into a concept called the Joint Embedding Predictive Architecture, or JGPA.
Right.
Specifically, we're looking at its multimodal version, VL-JEPA, and its stunning sort of world modeling application in robotics, VGPA-2.
And what this collection of research really represents is a fundamental theoretical upgrade. It's a shift in thinking. Instead of just building bigger and bigger systems to crunch more tokens, they redesigned the basic learning unit itself.
Okay, let's unpack this. Our mission today is focused on detailing how moving prediction from raw, specific, output-like generating tokens to these abstract, continuous representations, which is what JPA does, how that leads to radical efficiency gains.
And not just efficiency, but the ability to generalize with minimal data. And crucially, it enables a new level of what you could call common sense in physical robots.
Our sources are really rich today. They cover the full spectrum from theoretical physics all the way to practical robotics. We have technical papers detailing VL-JEPA and VGPA-2.
And plus that critical piece that outlines the underlying mathematical upgrade. The theory that makes these embeddings optimal. It's known as LLaVA, governed by something called the Statistically Informed Gaussian Regularizer, or SIGREG.
So we're really tracing the journey from abstract mathematics all the way down to a robot picking something up in the real world.
That's the plan.
Okay, so here are the key takeaways you'll carry with you after this deep dive. First, we'll show how VL-JEPA achieves stronger performance with 50% fewer parameters.
Which is a genuine paradox that, frankly, challenges the current AI scaling laws.
Second, we'll detail the technical breakthrough of selective decoding for streaming video, which lets the model only output text when the meaning actually changes.
Which saves a massive amount of compute and cuts down latency.
Third, we'll spend some crucial time exploring the theoretical magic behind why these abstract embeddings work so well. Specifically, this concept of the isotropic Gaussian distribution.
And why it is mathematically guaranteed to be the optimal structure for prediction.
And finally, we will show how VGPA uses this entire framework to create an action-conditioned world model, enabling truly impressive zero-shot robot planning.
All using a stunningly small amount of unlabeled data, just 62 hours.
Let's get into it.
Let's do it.
So let's start by establishing the inadequacy of the current dominant paradigm. Why is the classical way, the way that involves these massive token generative VLMs, why is that ultimately a dead end for efficiency?
Well, it works, right?
Yeah.
We should say that first.
It works, sure. You give them visual input, a text query, and they generate a response auto-regressively in token space. It's the state of the art.
It works well for tasks where time isn't really a factor, like, generating a long article or summarizing a document that's already written. But it is fundamentally inadequate for two main reasons that relate directly to efficiency, cost, and speed.
All right, let's start with the first one. Pure, unadulterated expense and waste. And I'm assuming this goes beyond just the fact that the models are huge.
It absolutely does. It's an architectural redundancy. These massive VLMs, they're trained to generate the desired response, let's call it Y, by capturing two distinct things at the same time.
Two things.
Yes. They have to capture the task-relevant semantics, so the actual meaning you need. But they also have to capture this massive, chaotic distribution of task-irrelevant surface linguistic feature.
Surface linguistic features. You mean things like tone, precise word choice, verb tense, that kind of thing.
Precisely. Whether the sentence is phrased actively or passively, the model has to spend huge amounts of computational effort modeling the distribution over all the possible ways a sentence can be phrased, even if those variations don't change the core meaning at all.
Can you give us an example?
Sure. Imagine asking a model to describe a video of a cat chasing a mouse. There might be, 100 perfectly accurate sentences?
The cat pursues the mouse.
A mouse is being chased by the cat.
The feline runs after the rodent.
Exactly. And the model has to dedicate billions of parameters and countless compute cycles to modeling the probability distribution over all 100 of those diverse token sequences.
Even though they all mean the same thing.
Yes, it's wasting effort modeling linguistic window dressing that doesn't actually impact the correctness of the output. That complexity modeling all these diverse token sequences that ultimately convey the same meaning, it just drastically inflates the training costs.
It's like trying to teach someone how to bake a cake by forcing them to memorize 1,000 different recipe cards, even though they all make the exact same cake.
That's a great analogy. The time spent modeling the variations in font size or grammar is completely wasted.
Okay, that makes perfect sense for expense. Now, let's get to the second reason these classical models fail in the real world. Latency.
And this is critical for real-time performance. Since they rely on autoregressive token-by-token decoding, the full semantic meaning isn't revealed until the entire sequence of tokens is complete.
So if you're tracking a live-action video, you need instant feedback.
Right. If a robot is trying to catch a falling object, waiting for the model to finish generating a sentence that says, the object is now 10 centimeters above the floor, is just.
It's too late. The object is already on the floor.
The sequential nature of it just introduces this unacceptable latency. You need continuous, dynamic, rapid semantic updates, not a delayed verbose sentence.
And what's fascinating here is JPA fundamentally avoids these issues. It changes the target of the prediction completely.
It completely sidesteps that language generation bottleneck. That's the core innovation, and it's why this architecture is sometimes called non-generative.
Okay, how?
So instead of predicting the raw, high-variance targets, the tokens, the VL-JEPA predicts a continuous embedding of the target texts, which we can call SY.
Okay, I want to focus on that distinction. When you say continuous embedding, you mean a dense vector in a high-dimensional space that represents the meaning, correct?
Exactly. This vector space is often called the abstract representation space, or the latent space. And model's entire training objective is to minimize the prediction error in this abstract space.
So instead of trying to hit that moving target of 1,000,000 possible sentence variations, all the ways a cat can chase a mouse, it's aiming for a single, fixed sort of semantic bullseye in a dense vector space.
That's a perfect encapsulation. All those 100 sentences about the cat and the mouse, they all map to essentially the same tight region in that latent space.
So the model is learning the idea of the cat chasing the mouse, not the words.
By learning in this abstract space, the model focuses only on the task-relevant semantics. It deliberately ignores or abstracts away that surface-level linguistic variability. This dramatically simplifies the target distribution during training, which makes the learning task much, much more efficient.
Okay, let's talk about the architecture. We have a visual encoder that takes the raw video and it maps it to a latent state representation, right? The core meaning.
And then you have a predictor that aims to hit the embedding of the future, or the target text. And this prediction is non-generative in the most important sense. The model is not forced to predict specific words.
It just has to land the prediction in the correct semantic region of the embedding space.
Correct. And this is done through what's called a joint embedding approach. Both the visual input, X, and the text target, Y, are mapped into the same latent space.
And I see in the sources that they often use something called info and C loss for this. Why is that specific loss function so essential here?
Info NC, which is short for noise contrastive estimation, is key because it introduces a crucial mechanism for contrastive learning. It basically ensures the quality of the learned representations.
How does it do that?
Well, mathematically, the info NC loss can be seen as having two necessary components. They act like a sophisticated quality control system for the embeddings.
Okay, what are they?
The first is a representation alignment term. This is the straightforward part. It just minimizes the distance between the prediction vector and the true target embedding vector. It makes sure the prediction is close to the truth.
So it ensures semantic fidelity.
Exactly. But the second component is a uniformity regularization term. This term actively pushes the embeddings within a training batch apart from each other. It maximizes the distance between dissimilar inputs.
Hang on, why push them apart? Wouldn't you want similar things to be close?
You do, but this is the critical mechanism to avoid what's called representation collapse.
The trivial solution.
The trivial solution, the lazy shortcut. Without this push, the model might find the easiest but totally useless solution, mapping all inputs, regardless of what they are, to the same single point. Everything becomes indistinguishable, and the model has learned absolutely nothing.
So the info and C loss, through that uniformity term, forces the model to use the entire latent space effectively. It makes sure that different meanings are represented by distinct, far-apart vectors.
Precisely. It maximizes the information density of the space. And crucially, compared to the sprawling high-variance token space loss used by generative VLMs, calculating the training loss in this simplified semantic embedding space is just inherently more efficient and stable.
So the core of the breakthrough isn't just prediction, but making sure the space in which you predict is mathematically robust.
Absolutely. We've moved from a generation problem, which is outputting words, to an alignment problem, aligning vectors. And that is just much faster and cheaper to solve.
All right, let's transition from that theoretical shift to the tangible, quantifiable benefits. The first result from VL-JEPA that really shook the community was what they call the parameter paradox.
This is where we see the efficiency of that semantic focus really paying dividends. In a strictly controlled comparison, and I mean, they use the exact same vision encoder, the exact same data, the same batch sizes as standard VLM training.
Okay, so a true apples-to-apples comparison.
Right. VL-JEPA achieves stronger overall performance across a range of tasks while requiring 50% fewer trainable parameters.
50%. That's monumental. That's half the GPU hours, half the energy consumption, half the infrastructure for deployment. This doesn't just reduce cost, it changes who can even do this kind of research.
The financial implications are staggering for any organization running these models. We're talking millions of dollars saved in cloud compute costs, a significantly reduced carbon footprint. And yet, the result seems to fly in the face of the scaling laws we've all internalized.
The idea that performance is just tied to parameter count.
Exactly.
So why can't it be stronger with less? How does the scaling law seem to bend here?
Well, it proves that all that model capacity was being wasted before. The classical VLM was forced to dedicate a massive chunk of its parameters to handling that hyper-complex, high-variance token distribution.
The linguistic variability we talked about.
Right. VL-JEPA just eliminates that entire problem. It dedicates its resources only to learning the abstract, low-variance semantic structure. The parameters it does have are used far more effectively because they are focused purely on meaning, not syntax.
So the model becomes this highly focused, semantically optimized machine. But, okay, if all the heavy lifting is done in this abstract space, we still need to generate text sometimes. Where do the words come from?
That's where the inference architecture maintains its efficiency. At inference time, you don't need that massive, wasteful, autoregressive decoding pipeline. Instead, a very lightweight text decoder is invoked, and only when it's needed.
And its only job is to translate that stable, pre-calculated embedding into a sentence. Here's where it gets really interesting for me. Let's detail the specific technical solution for online streaming inference, which they call selective decoding. This seems absolutely crucial for any application involving continuous video.
It's the heart of robotics and ambient AI. The problem context, as you said, is real-time video. If you're building procedural assistance for smart glasses or monitoring equipment with a camera, you need ultra-low latency.
And the traditional methods are just wasteful?
Completely. They use uniform sampling. They just decode text every second or every fixed interval, regardless of whether anything meaningful is actually changed in the scene.
Right. So if I'm streaming a long video of myself organizing a shelf, most of that video is static. I don't need a caption every second saying hand is near the blue box.
Exactly. The semantic content is stable, but the uniform sampling mandates this continuous, wasteful decoding. VL-JEPA's solution is adaptive selection, driven by embedding-guided selective decoding.
Okay, break that down for us. What's the intuition behind it?
It uses a clustering technique called agglomerative clustering, but with a twist. It applies temporal connectivity constraints to partition the embedding sequence over time. It's looking for segments of high intrasegment monosemanticity,
Which is a fancy way of saying
low semantic variance.
Yeah.
The model continuously generates these embeddings from the video stream. If the predicted embeddings within a certain time window are all extremely close together, low variance, It means the semantic content, the meaning of what's happening, hasn't changed.
The state of the world is stable.
Right. And the moment the variance spikes, that signals a critical event, a new action, a change in an object's state. Something important has happened. That's the trigger.
So it only decodes text when the meaning changes.
Precisely. It decodes once per semantically coherent segment, capturing the essential information while dramatically cutting the overall decoding cost. It's a dynamic, event-driven system, not a rigid, clock-driven one.
And they tested this on a really tough data set, right? The Ego X40 validation set.
Which is all long-form, real-world video streams. Complex, noisy data. And the quantifiable result is powerful. The selective decoding approach consistently predominates uniform sampling.
Meaning for the same level of quality, you need way fewer decodes.
Significantly fewer. The sources specified that this mechanism reduces the number of decoding operations by approximately 2.85 times.
2.85.
Let's contextualize that. If uniform decoding needs to happen once per second, that's 1 hertz, to get a baseline performance. Selective decoding achieves that same baseline performance decoding only at 0.35 hertz.
So 1 decode operation roughly every 3 seconds to get the same useful information. That's a radical gain in efficiency for any continuous online application.
And beyond efficiency, this rich embedding space naturally supports a unified generalist approach. VL-JEPA can handle a whole range of tasks without needing a specialized architecture for each one.
So open vocabulary classification, VQA, and text-to-video retrieval. It's all built on the same foundation.
Correct. For retrieval, for example, it's purely based on vector similarity. You encode your text query, you encode the candidate videos, and you just rank them by how close their embedding vectors are. It's incredibly fast and effective.
Let's look at the performance snapshot. How did the initial model, VL-JEPA base, do on zero-shot tasks right after its big pre-training stage?
The zero-shot performance really confirmed the quality of the learned representations. Across 8 video classification and 8 text-to-video retrieval datasets, VL-JEPA base demonstrably surpasses foundational models like SICLIP, SIGLIP2, and Perception Encoder.
So even before fine-tuning, the quality of the vision-language alignment is just superior.
Exactly. And once they do perform supervised fine-tuning, making it VL-JEPA PAS-FT, the model becomes a powerhouse. Despite having only 1.6 billion parameters, which is, relatively small in this world, it achieves comparable performance to much larger classical models like InstructBLIP on major VQA datasets.
And again, it's not generating those answers autoaggressively, is it?
No. For VQA, it uses its inherent structure. It encodes the possible answers into the latent space and just picks the one that's semantically closest to the predicted embedding. It's selection, not generation, which is just far, far leaner and faster.
So we've established the incredible practical benefits. 50% fewer parameters, almost 3 times faster decoding. The system is lean. But now we have to ask why. Why are these embeddings so robust and useful for prediction? We need to go back to the source, the mathematical search for the optimal latent space distribution.
And this is where Jan LeCun's long-standing vision for building these accurate, non-generative world models really comes into play. It ties directly into pure mathematics. The goal is to learn representations that capture the actual structure of the world, the underlying geometry of data, not just superficial patterns.
They want to model the state of the world represented abstractly.
Precisely.
So we're aiming for a set of embeddings that are not just compact and semantic, but mathematically ideal. What did the researchers identify as that mathematically optimal shape?
What's fascinating here is they identified that the optimal embedding distribution is an isotropic Gaussian.
Okay, let's spend some time on this because this is the theoretical linchpin. We all know the Gaussian distribution, the bell curve. What does isotropic add to that?
Okay, so think of the embedding space as a cloud of billions of data points in a high-dimensional room. An isotropic Gaussian is like a perfectly spherical, round cloud.
Perfectly round.
Isotropic literally means same in every direction. If you were to shine a light from any angle and look at the 2-dimensional shadow it casts, that shadow would always look the same, a perfectly round circle. The variance is uniform along every single dimension.
And the alternative, which I guess is what most real-world data would produce naturally.
The opposite is an anisotropic Gaussian distribution. This would be stretched or squished. It would look like an elongated ellipsoid, like a football or a cigar shape.
This is problematic because it has preferred directions.
What do you mean by preferred directions? It means the space is distorted. If you project it onto its short axis, the points are all squished together and they're hard to tell apart. If you project it onto the long axis, they're super spread out and might contain a lot of noise. Anisotropic means different in different directions.
So why does the math strongly favor the perfectly round isotropic structure?
Well, the isotropic Gaussian offers a powerful theoretical guarantee. Among all possible data distributions, it uniquely minimizes the integrated square bias for several common predictors used in machine learning, like k-nearest neighbors and kernel regression.
Let's unpack that. Why does a stretched distribution, the anisotropic one, introduce bias?
Imagine you have that stretched, football-shaped distribution. When a new input comes in, the distance metric you're using, like Euclidean distance, is inherently distorted. The space has been squished in some directions and expanded in others.
So if you try to find the nearest neighbors to classify a new point,
The results will be unreliable. The distance calculation is biased because the features that happen to lie along those stretched axes are unfairly weighted compared to the features along the squished axes. The model is implicitly prioritizing certain features just because of how the distribution got distorted during training.
I see. So forcing the embeddings into that perfectly round, balanced isotropic shape guarantees that every future dimension is treated equally.
Which mathematically ensures that any downstream prediction tasks will be operating with the lowest possible integrated square bias. It makes the model far more reliable and generalizable.
That's some impressive mathematical rigor. But here's my challenge. Real-world video and language data is messy. It's correlated. It's definitely not a perfect sphere. How do they actually enforce this optimal shape without everything just collapsing?
That is the main technical breakthrough detailed in the VL-JEPA paper. The solution is the SIGREG term, the statistically informed Gaussian regularizer.
Okay, SIGREG. How does it nudge the encoder toward that perfect isotropic shape while still letting it capture the complexity of the real world?
It uses a mathematical cheat code, basically, based on something called the Kramer-Wold theorem.
Okay.
Comparing two full high-dimensional distributions is computationally impractical. It would take forever. The Kramer-Wold theorem provides a shortcut. It states that a multivariate distribution is completely determined if all of its one-dimensional projections are known.
So they don't look at the whole 10,000 dimensional cloud, they just look at the shadows it casts.
Precisely. Think of the embedding space as a multifaceted diamond. To check if the diamond is perfectly cut, you don't need to measure every single point inside. You just need to shine a light from many different angles and measure the resulting one-dimensional shadow, or projection.
And if all of the shadows look like a perfect 1D Gaussian bell curve, then the diamond itself must have a perfect isotropic Gaussian shape.
That's the analogy. SIGREG projects the high-dimensional embeddings onto many random 1D directions. For each projection, it examines the resulting distribution and compares it to what the projection of a true Gaussian should look like. And it uses a statistical test to measure that mismatch.
And that mismatch becomes the loss that the encoder has to minimize. It's forced to adjust its parameters until it minimizes both the prediction error and the deviation from that perfect shape.
And that is the definition of VL-JEPA. It's the combination of the usual JEPA prediction loss plus the SIGREG Gaussian regularizer. It ensures the model learns predictive power while simultaneously optimizing the geometry of the space it learns in.
And what are the practical advantages of using this deeply theoretical approach compared to the old ways?
The elegance of the implementation is key. VL-JEPA avoids all the old clunky heuristics that used to plague self-supervised models trying to prevent collapse.
Things like stop gradients or teacher-student models.
Exactly, all that complexity. VL-JEPA prevents collapse by construction, not by adding tricks. The sources highlight that it's extremely stable. They successfully trained roughly 50 different models across 8 different architecture families with it.
And the researchers give us just one knob to turn to manage this whole balance.
Yes, the simplicity lies in the lambda trade-off. Lambda is the single hyperparameter that controls the balance between the two objectives: prediction accuracy versus distribution regularity. It gives researchers a direct, intuitive, and mathematically sound way to tune the underlying structure of their world model.
We've established the mathematical foundation. The result is this robust, efficient, semantic embedding space. Now, let's pivot to the ultimate real-world stress test: robotics. VL-JEPA 2 applies this whole principle to the massive domain of video and action to bring genuine common sense to physical machines.
And the need for VL-JEPA 2 really stems from a fundamental deficiency in traditional robotics, which is the lack of intuition. For a human, knowing that applying force here will cause an object to tip over there, or that a fragile box needs gentle handling, that's just intuitive physical common sense.
But robots, trained only on specific trajectories, they lack this intrinsic predictive knowledge about cause and effect. They lack an implicit physical world model.
Exactly. VGPod 2 is designed to learn that world model. It's a self-supervised learning model that learns by predicting the missing parts of unlabeled video sequences. It's representation-level prediction for physical dynamics.
By accurately predicting what should happen next in the abstract latent space, it captures the key dynamics, the physics, the relationships between objects and actions.
Right, which allows it to predict the consequences of its own actions.
So how did VGPod-2 achieve this unprecedented strength? The sources detail some key ingredients for scaling beyond the original recipe.
There were several major scaling interventions. First, just the sheer scale of the data. They increased the dataset size massively, from 2 million to 22 million videos, leveraging over 1 million hours of internet video.
1 million hours! That included things like ImageNet, egocentric video, and exocentric videos from places like Kinetics and YouTube.
Right, and crucially, the massive raw YT temporal 1B, or YT1B dataset,
Which is over 1 billion videos from YouTube. That sounds like a minefield of noise and low quality. How do you feed a model that much uncurated internet chaos without just diluting the learning signal?
That's a great point. And the data cleaning challenge was substantial. Uncurated data can absolutely kill performance. They employed a sophisticated retrieval-based curation pipeline for YT1B.
What does that mean?
They extracted scenes from the YouTube videos, computed embedding vectors for each one, and then used a cluster-based retrieval process to select only those video scenes that semantically match the characteristics of high-quality pre-existing datasets like Kinetics.
So they used a smaller, cleaner dataset as a filter for the massive, noisy one. They selected for quality and relevance at scale.
Precisely. This ensured the model benefited from the sheer volume without being drowned by irrelevant junk. And beyond data, they scaled the architecture capacity itself from 300 million parameters to over 1 billion for the encoder.
And that scaling still paid off, even with this more efficient approach.
It did. It confirmed that this kind of self-supervised learning benefits significantly from larger capacity when the learning objective is clean. They saw cumulative positive improvements with scaling.
Okay, let's talk about the implementation for robotics. This involves a crucial two-stage process leading to the action-conditioned world model, VL-JEPA 2AC.
Right. Stage 1 is the generalized representation learning. VL-JEPA 2 learns these robust vision representations from that massive 1 million hours of action-free observation data. It's just watching the world and building an implicit physics engine.
And stage 2 is where the model is specialized for action and control.
Yes. In stage 2, that robust, pre-trained video encoder is frozen. Its world knowledge is locked in. Then a new, much smaller, latent action-conditioned world model, the VL-JEPA 2AC part, only about 300 million parameters, is trained.
And this secondary model predicts the representation of the next video frame, but conditioned on the robot's action.
And its previous states. It's basically the model asking itself, if I am state A and I apply action X, what will the world look like next in the abstract?
It's learning the immediate consequence of its own actions.
And the most startling part of the source material involves what you could call the droid dataset miracle.
I was struck by this. Traditional methods require thousands of hours of expertly labeled, curated, successful demonstrations. VL-JEPA 2AC was trained using less than 62 hours of unlabeled robot videos from the droid dataset.
62 hours, that's minimal to the point of being revolutionary for robotic data collection. And the lack of labeling is so important, right?
Because the data consisted of these short videos of a robot arm, including successes and failures, along with the corresponding data. The model doesn't need explicit reward metadata saying you succeeded or you failed.
It just learns the dynamics of the world. The consequence of an action, regardless of whether that consequence was good or bad for a specific task. That's true common sense.
That knowledge of consequence, what happens when you tip the cup, is the foundation for prediction and therefore for planning.
So what does this 62 hours of learning actually enable in the final application phase? Zero-shot planning.
This is the payoff. VL-JEPA 2AC enables robots to perform prehensile manipulation tasks, like pick and place, using planning with image goals. And crucially, they achieved zero-shot generalization. They deployed VL-JEPA 2AC on Franca arms in 2 different labs, performing tasks without collecting any data from the robots in those specific new environments.
Wait, so 62 hours of general training data and then it can walk into a completely new lab setup and just start working? That changes the fundamental equation of robotic deployment.
It's the definition of true adaptability. The underlying world model, learned from the web data and refined by those 62 hours of interaction, provides such a robust representation that the robot can just infer the optimal action sequence by minimizing the semantic distance between its imagined future state and the goal state.
And that leads us to the most dramatic quantitative result.
Yeah.
The massive efficiency contrast with competing models like Cosmos.
Oh, absolutely. Speed is everything in robotics. Cosmos, which is a state-of-the-art video generation model, required a brutal 4 minutes to compute a single action.
4 minutes for one action.
Yeah. So a simple pick-and-place task that needs 10 actions would take nearly an hour just to compute, making it completely useless for any real-world application.
And VL-JEPA 2AC.
By contrast, the VL-JEPA-2AC latent world model required only 16 seconds per action. And that was while using 10 times more samples in its planning step than Cosmos, which actually yielded higher performance.
So it's reported to be 30 times faster than NVIDIA's Cosmos model in some key benchmarks. The choice to predict abstract embeddings over generating pixels translates directly into real-time capability.
And we should confirm that the massive pre-training also paid off in traditional vision benchmarks.
It did. The model achieved strong results on visual understanding tasks requiring complex motion reasoning, and it achieves state-of-the-art performance on human action anticipation, predicting what a person is about to do. It clearly learned robust, general-purpose vision representations that generalize across all sorts of tasks and environments.
So, to synthesize what we've discussed, the VL-JEPA family represents a unified generalist model that achieves efficiency by design. It handles generation, retrieval, classification, VQA, and robust world modeling for action.
And there's a distinct anti-LLM vibe here, at least for perception tasks. This efficiency focus, avoiding token generation, maximizing latent space utility, it signals a major shift away from relying on massive, slow, autoregressive models where quick semantic understanding is paramount.
It's a move toward structural intelligence over sheer expressive capability.
That focus on latent space utility is the signature of this work. However, before we declare victory and deploy these robots everywhere, we have to acknowledge the current hurdles. What are the practical challenges remaining?
Well, the first major limitation is the data reliance. VL-JEPA-2 is trained solely on visual data images and video. This limits its ability for crucial multisensory tasks.
Like tactile manipulation or hearing things.
Exactly. Fine-grained tactile manipulation, detecting material properties through touch, processing auditory cues. A fully realized robotic world model needs to go far beyond just vision.
That's a critical gap. And what about complex, long-horizon tasks? We saw success in short-horizon pick-and-place. Can it plan how to assemble a piece of furniture?
Long-horizon planning is still a huge challenge. First, all autoregressive prediction systems suffer from error accumulation. The further out you predict, the less accurate it gets.
And the search space just explodes.
Exactly. The action search space increases exponentially with a longer planning horizon. Finding the optimal sequence of 50 actions is computationally intractable without breaking the task down into smaller sub-goals.
And the current system relies on visual goals.
Right.
An image of what you want the world to look like.
Right. If you want the robot to clean the kitchen, you have to show it a picture of a clean kitchen. Future work is absolutely needed to align these models with language models to enable true task specification via natural language.
Like, please empty the dishwasher and put the dishes away.
Exactly. And finally, there's just the messy reality of physical deployment, the integration challenge. VL-JEPA 2AC is the brain, but it needs a body. It requires smooth interoperability with motor controllers, real-time sensors, task schedulers, all in dynamic, unpredictable environments.
That systems engineering part is often overlooked.
Despite those limitations, the progress demonstrated here, scaling self-supervised learning from web data and pairing it with minimal interaction data, is fundamentally crucial. It provides a scalable, efficient, and theoretically robust framework for developing AI that can perceive and act in the physical world.
This has been a truly deep dive into the guts of how to build smarter, leaner, and ultimately more useful AI. We started by seeing how the JEPA principle transforms resource-intensive token generation into this highly efficient, abstract embedding prediction.
Which alone cut the parameter count by 50% and yielded massive speed gains with selective decoding. And we learned that this efficiency is supported by a foundational theory, VL-JEPA and SIGREG. This mathematical approach guarantees the optimal latent space geometry, that perfectly balanced isotropic Gaussian, which minimizes bias and maximizes generalization.
And this all culminated in the VL-JEPA 2AC world model, which proved you can achieve unprecedented zero-shot planning capabilities for physical robots, leaping past speed bottlenecks that crippled earlier models.
The core lesson is clear. The fastest path to common sense isn't always brute force scaling, but choosing the most mathematically efficient space in which to represent and predict reality.
And if we connect this to the bigger picture, the quest for common sense in AI means moving beyond just generating fluent language or memorizing datasets. It's fundamentally about robustly predicting the abstract dynamics of the world, whether that's linguistic interactions or physical cause and effect. And that raises an important question.
Which is,
If a robot can learn to predict the physical consequences of its actions, zero shot, using abstract embeddings shaped by perfect mathematical principles, how long before that predictive capacity is applied not just to pick-and-place tasks, but to predicting human intent or economic changes or complex social consequences? The core architectural recipe for a dynamic world model is now out there. The choice now is, what worlds, what spheres of consequence will we model next?
that's a powerful and slightly provocative thought to end on. For you, the listener, if you want to dig deeper, I highly encourage you to explore the concept of isotropic Gaussian distributions in high-dimensional space, or search for more information on the trade-off between generative and non-generative prediction in self-supervised learning.
Thanks for joining us for this deep dive.
We'll see you next time.